as the millimeter wave measurement needs increase in network analysis. They're for both device model development validation, harmonic analysis, and then devices are used in many applications. There might be some need for a VNA that can cover a wider frequency range. And we're going to talk about one such structure that has an on-wafer emphasis with a single calibration capability to cover that frequency range of about 220 gigahertz. And we'll examine a number of performance quantities of interest. So the outline of the talk is a little bit of background on why a broadband coverage might be interesting and some commonly important parameters. Go over the architecture of this particular instrument, both on the stimulus side and the receiver side, and the more unique part of it is probably the RF interface, and then go over some measurements and performance. So why broadband measurements if I'm only interested, say, in a D-band radio, for example, or something like that? In model development and verification, we heard about some of that this morning, there's often a desire to cover a much wider frequency range, if for no other reason, physicality analysis and some kind of asymptotic studies of those model elements. There may be interest in out-of-band behavior and kind of situations like this. This is a reflection measurement. Someone's designing a little radio to work around 140 gigahertz. And because of impedances presented at the ports of the device, there's some really interesting activity down around 40, which if you're only measuring there, you might not miss. And while in and of itself, it might not destroy device performance, it could cause some really interesting efficiency behaviors and all kinds of interesting spurs running around in the device being tested. There may be harmonic regulatory emissions requirements, which is a little bit interesting. If someone's doing a 60 gigahertz radio and they're told they need to test at 120 emissions, it might happen. And there are some countries in the world already mandating that kind of analysis. And then, of course, many devices may be used in a number of different applications, so the broadband coverage might matter. And what's currently done often is, and still has to be done even with the structure I'll talk about in some limits, is stitching together measurement data from different bands with different setups typically and different probes. In some cases we'll hear more about the calibration aspects in another talk later. But you can easily run into situations like this in stitching together the data where there's a step which in terms of the uncertainties is justifiable, but trying to handle that in model processing and other kinds of analytics can be a bit of a daunting challenge. Discontinuities don't tend to make people happy for some reason. So this work focuses on something to try to help in that area, and that's really a VNA extension to allow reference planes, single reference planes running up to about 220 gigahertz. And much like a lot of existing structures from various vendors, there's a sort of a multiplexing scheme going on where you combine multiplied sources from different paths and multiplexed receivers in some way, shape, or form. And a number of ancillary kinds of topics that don't get as much attention, but I'll spend a little time on in terms of power control and power leveling, as well as LO leveling to try to improve stability of the measurements. So examining a little more detail on that picture, the source-related kinds of multiplexing are shown in purple. And so you have some signal energy coming in here for baseband, and then a series of multipliers that get muxed into this main hotline to cover the higher frequencies. The receive side is in red, and so there's a single reflectometer here to cover the high end, and then some baseband reflectometers to handle the lower frequencies. Zeroing in that a little bit, on the source side, just a series of 4 multiply chains, and the bandwidth limited by power amplification and the multipliers themselves. Those all get multiplexed with some coupling increasing as we go up in frequency for the obvious reason it's harder to get more power above 200 gigahertz than it is below 100. The receive side's a little bit simpler. There's just one reflectometer covering a little under a decade with a sort of modest multiplication number on the LO and a fairly flat conversion efficiency over that range. Lower frequencies are handled back at the base VNA. Now the interface is a little more of a challenge if one thinks about it. So there are 1 millimeter and 0.8 have been around for quite some time. But as these dimensions get smaller, surprisingly, at least to me it was surprising, the first thing that became a problem with the traditional threaded connector were the torsional forces, trying to thread that nut onto the pin. And particularly if you use a split finger female collet, just the mechanical stress on that get to be pretty substantial. So this particular structure was chosen. It's still coaxial mode. And this is the female conductor you can see in the middle there. The outer conductor diameter is about 0.6 millimeter. And you can see the image of what looks traditionally like a waveguide flange, and indeed that's what's used for alignment. With related to a recent IEEE standard, it has alignment pins that handle that positioning before the male pin mates with the female collet that's shown right there. And there's a picture of the male pin on this picture, and you can tell it's a split contact, so it maintains spring force as it mates with the female, so you get the DC conductivity that you're going to need for biasing and for the 70 kilohertz coverage on the low end. So up top here is just a connector repeatability kind of measurement. This is, again, a difference of final to initial reflection coefficient expressed in dB terms. And this is after 100 reconnections measuring the same device at a modest return loss kind of level. So bouncing around in the minus 60-ish, minus 50-ish kind of dB range. And that compares reasonably well to 0.8 and 1 millimeter connectors in their respective frequency ranges, somewhere around minus 50 or so for typical kinds of results. 1,000 reconnection experiments have been done. I didn't plot that data here, but it gets a bit worse as one might expect, and you can see a little metal shaving showing up after those connections. But about a half dB variance in raw source match, using that as the metric to compare before and after that cycle of lifetime measurements. So next going to look at some measurements of interest, really just to show or try to characterize some of the instrument behaviors. Looking at noise, drift, admittedly in a classical vendor kind of way of looking at drift. And then spend a little bit of time on power control. As I said, that isn't covered as often in this kind of presentation. I want to spend a little time on that. And then noise floor, and again, one typically isn't going to be measuring a high rejection filter or something over these kind of bandwidths. But if you are testing a device that needs a very low drive level to avoid compression, say minus 40, minus 50 dBm, the actual noise floor does sort of matter for SNR reasons. So trace noise, and there are a couple of different ways of looking at this in keeping with, I guess, the industry. An RMS kind of quantity, so multiple sweeps are processed statistically for that, and that should be megahertz, not gigahertz, as you probably guessed. But holding below about 10 millidB, at least up to 200 gigahertz or so, which is in keeping, and this is sort of classical kinds of numbers below 100 gigahertz. And a plot here on a different scale, this is real time, just a single trace if you're doing, say, a single sweep and want to see the variation after a normalization. At scale, 100th of a dB or so, and this is in a sort of classical kilohertz kind of IF bandwidth. Stability, just of looking at a through line in this case, important since it sort of relates to how often recalibrations have to occur. It's not a perfect metric, since it's a specific kind of device, but it can illustrate a few things. And this is in a modestly controlled laboratory environment, so not super tight and not outside or anything like that. But magnitude is shown on the left, and on the order of 7 or 800ths of a dB up to 226. And this same kind of vector delta reflection is shown on the right and holding in the 40-ish, 50-ish kind of dB range over that 24-hour cycle. And that sort of leads into a little side discussion in that it doesn't really help much for direct device measurements, but it was handy to have something internally, a through line in this particular interface kind of structure. And so it actually looks like a waveguide part from the outside, but it is a coaxial through line through the structure. And as you might guess, pin depth control is much more important than at lower frequencies, and this is holding about a 5 micron tolerance on that. And there is a coaxial line with dielectric inside, so there is a phase variation of the structure with temperature. But it is an interesting device, just as a passive artifact, and use that for some verification kinds of topics. Looking at power control, I mentioned earlier there are a lot of cases where not so much a power sweep, although that's interesting for compression kinds of studies, but just to stably hold this power at a low level where, for example, a bare transistor isn't going to compress. Having some decent control range can help. And this is a power sweep just of a reference signal, so you can view this as a proxy for port power, sweeping from -55 to -10 at 220 gigahertz. But the linearity is reasonable over that range, and this wasn't calibrated at that particular frequency by itself. Now, that was with IF leveling, this previous chart, so you're required to have some kind of frequency plan that's commensurate with that to generate an IF. But oftentimes when you're measuring at least certain frequency conversion devices, you may not have an IF available. So there are RF leveling taps in all of the paths, which, because they're broadband, there isn't nearly as much control range available. This is only over -30 to -10, but you get reasonable agreement between the two, just natively from that. And at the low levels, sort of come back to a trace noise kind of quantity. At that kind of drive level, obviously your SNR gets worse, so you hope the, I guess, raw characteristics of the data don't degrade too much. So this is in a slightly narrower bandwidth, but at -50 dBm drive, so a few hundredths of a dB up to 400ths of a dB in that particular measurement. Source harmonics may or may not be important depending on the linearity of the DUT being looked at, but this is a plot of the output harmonics expressed relative to the desired output frequency. That's why they're sort of funny units. But so the dominant is the 2/3, as one might expect, since it can be in band at the higher end of the frequency, but they're holding better than -15 dBc for the better part of the band. And this was measured with a classical harmonic-mix-front-end spectrum analysis tool. And noise floor, the down converter efficiency is again relatively flat, but at the front end you do have some loss from the interface itself and the coupling structure and so on, so there's a bit of an effective roll-up, and so this is expressed in absolute power terms, and this is in a 10 hertz bandwidth without any statistical processing on that data. So with some basic network kinds of measurements, there's always the interest to bring up some of the lower frequency VNA tools to the broadband structure. Among them is a true mode stimulus kind of topic for differential devices, which are always popular. And really it's having two coherent sources in the phase programming between them. The tricky part, of course, is there's a lot of multiplication going on after that base synthesis level. So you are going to be stressing both the resolution of the phase control and the stability of the networks. And so this is a plot of phase sweep at 220 gigahertz. And you can see some little step-like structures, and that's really running into resolution kinds of limits in that kind of setup. And the stability of that phase relationship, let's say I want to drive a pure differential device over about a 1 hour period, and there's a few degrees of variation. Part of that's due to just the external environmental, but again, that sort of represents the effect of the big multiplies that are in play here. And finally, a measurement example, this just of a multiplier that wanted to be characterized, happens to be a V-band to G-band, full band multiplier, and just comparing against a harmonic mix spectrum analysis kind of measurement to get a handle on the relative performance and the relative uncertainties. So nothing too surprising in the measurement. The output power is decent for this DUT, around 0 dBm. So the basic harmonic mixer on the spectrum analyzer is being used had some linearity issues, which contribute a little bit to the uncertainty there. One can always pat it down, but then when one's fighting the signal to noise, so it's a little bit of a trade. And there's a power calibration issue that comes into play there of the native factory calibration of the mixer versus at the interface you're testing it to. So there's a little bit of an improvement in that regard. But there does seem to be reasonable agreement over the frequency range, as shown here, and certainly within the uncertainty overlap. So have presented a broadband VNA structure covering a larger frequency range that might have some advantage in these classes of model development and covering multi-band devices without a lot of the data stitching and other chores that might be required. And sort of central to it, like a lot of the other broadband structures that exist at lower frequencies, is a multiplex source and receiver chain. And there's a slightly unique coaxial mode, kind of flange-based structure to facilitate that interconnection. That's all I have. Thank you for your attention. Oh, certainly. It's a continuous sweep and a continuous calibration covering both of those interfaces. So both a phase calibration, if one was implementing that, and just the standard calibration certainly map through. Have to let this guy answer that question, but there are probes that will be available for this, for standard kinds of pitch patterns. Yeah. Yeah, it looks nice. But,